Hello again folks, Lecturer Joe here. We're going to take a look today inside a PLC to see what's going on. So here we've got an Allen Bradley Micrologix 1200 PLC which no longer works, so we're going to rip it open and see what's happening inside. So the front cover here drops off like so and leaves these parts behind. So we'll take a look at these parts in turn and see if we can tie them up to the kind of schematic diagram, or like a block diagram if you like, of what we expect to find inside a PLC. The first thing we can see from the front of the PLC here is the screw terminals. These are the input terminals and these are the output terminals. So wired into these input terminals are any devices that form an input to the PLC. So that's a push button or a sensor. And connected to the output is anything that, whatever it is you want to turn on and off of the PLC. It could be a conveyor belt, a fan, a pump, a motor, a light, whatever. So outputs are connected here, inputs are connected here. There are also a couple of power connections here. You can see 24 volt DC and common. So on the front also we have a row, you can ignore this writing here, we've got a row of tiny LEDs spread along here. Now they're obviously not illuminated at the minute because the PLC is in bits, but we have 14 LEDs in a row here and 10 LEDs in a row here, and these equate to 14 digital inputs and 10 digital outputs. So there's an LED for each input and an LED for each output. And in the normal mode of operation for the PLC, if an input is present at if someone has pushed a button that's connected to input 6, you'll find that LED 6 is illuminated. And if the PLC has turned on outputs 2 and 4, you'll see that these LEDs for outputs 2 and 4 are illuminated. So these are a visual indication of which inputs are on and which outputs are on at any given time. And that's really useful when you're working at PLCs, if you're fault finding, to figure out which inputs and outputs are on. There are also a series of LEDs running diagonally here, which are a little bit hard to see because it's been scribbled over. But these are for power. So the power LED here will be lit if the power supply to the LED is running okay. There's then a run LED. That will be illuminated if the PLC is in run mode. In other words, when you send your program to the PLC, the program can live inside the PLC but not be executed, not be run, in other words. So it's possible for the program to be inside the PLC but the PLC not doing anything. When you put the PLC into run mode, it then executes your program permanently. And when it's in run mode, you'll see that little LED lit. The next one I think I can see there is, I think it's fail, F-A-I-L. So if there's a problem, if the PLC internally detects a problem with itself, there are a lot of self-checking mechanisms built into a PLC. That will be lit up to show that there's a problem. The fourth LED down there, I'm sure you won't be able to read it there, but it says force, F-O-R-C-E. And this refers to the fact that the PLC is in force mode. Now force mode is where you can override the normal operation of the program and tell the PLC via a laptop connection to manually turn on some of the outputs. So even though the program is running and at that particular time certain outputs aren't on or off, you can force them on or off for test purposes. But you got to know that the PLC is in force mode then, which is why we have an LED here. If we put it into force mode, this LED illuminates. The other two lights are just for communication, so we see them flashing if the PLC is communicating with another device over a network. So that's pretty much all there is to see from the top plastic cover, if you like. So let's pull that off. And you can see here that the LEDs are not built into the plastic cover, but there is a little cylindrical piece of plastic glass, piece of perspex that conducts the light. So these are really just windows that you see here, and the LEDs are mounted on the board itself. So with the cover sitting like that, there are the LEDs mounted on the board there in a row. Input LEDs, output LEDs, and the other LEDs that we mentioned for power, run, force, etc. are here. So the LED lives on the board, not on the plastic cover, but these simply conduct the light up to the front so we can see the status. So this is the first board we see when we open it up, and this board is actually piggybacked on top of another board. If we dismantle that, we can see these boards fit together through these connectors here. So the two boards just snap together and one can communicate with the other through this connection. So let's see what we can see at this point. And the most obvious thing to see inside this board are these white devices here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got 10 little white boxes of some description here. And these tally up with the 10 outputs on this PLC. So this PLC can turn on and off 10 separate devices. It has 10 digital outputs. It has one of these for each output, and these are mechanical relays. So they're really an electromechanical switch, if you like. Inside each one of these is a physical switch that will close to turn on the output. So you've probably come across relays before that are considerably larger in control panels and the like, but there's an actual miniature relay for every one of the physical outputs there, hence the reason why we have 10 across here. If you haven't come across relays before, a relay is an electrical contact, a switch if you like, but rather than, unlike a light switch you have at home that you got to poke your finger on in order to get the switch to close and bring on the light, with a relay the switch is activated not by you physically pushing it, but by magnetism. There's a coil of wire that you can connect the supply to, and when you connect your supply to that coil of wire, the wire produces a magnetic field, and that magnetic field is what pulls the switch contact in. So there's one of these relays for every one of the outputs. The next thing we can see is a bunch of things that seem to be physically near the input screws. So we have these running along here and these running along here, and together these form devices known as opto-isolators. So every one of the input terminals on the PLC is connected through to the actual brain, the actual microprocessor, using an opto-isolator. So let's look at what that is. So your PLC has inside it a microprocessor, which is essentially the brain, and then you come along and you wire things into the PLC like this. Inputs from the real world, push button switches and sensors and the like. Now, if internally your connection from the outside world went straight to the microprocessor, there would be a danger that any kind of electrical noise that this line picks up, any disturbances, would cause this microprocessor either to just hang up, the way your PC sometimes does and you got to reboot it, or actually destroy the processor. So any kind of static or any sort of unusual voltages that are picked up in this line would damage this microprocessor and ultimately destroy your PLC. Now in industry, it's not so much the cost of the PLC that we're worried about, it's the cost of the downtime in terms of manufacturing when the machine stops because the PLC is packed in. So it's of paramount importance that there's nothing, no signals from the outside world that can cause this microprocessor to hang up. And that's where the opto-isolators come in. So to avoid this microprocessor hanging up, we have this kind of arrangement inside the PLC. When your signal comes into the PLC from your push button or whatever, it passes through an LED. The LED emits light, and that light shines onto a phototransistor. The phototransistor then switches on and puts the signal into the microprocessor. So input on, signal into microprocessor, but midway here the electrical signal has been converted from electricity into light and back to electricity again. And the advantage of that is that any kind of spikes here, spiky voltages that are present, can't go through to the microprocessor and cause that to hang up. Now you don't see this inside the, well, you don't see LEDs shining inside the PLC, because this whole thing is encapsulated into what looks like an IC, an integrated circuit, and that's what you have here. So these are multiple opto-isolators, one for every output, and you can actually see, if you look closely, that the legs on them are in pairs, 2, 2, 2, 2. And that's because on one side you have the LED, and on the other side you have the phototransistor. So inside here there's a tiny beam of light passing across, meaning that the electrical signal you've applied outside, that same electrical signal never makes it to the processor. It's converted the light back to electricity into the processor, so no noise can make its way through. So every output has a relay on it, and every input has an opto-isolator. So what about the brain itself? Well, if we flip over this board, we see the main IC, the main microprocessor here. And this is pretty much like the CPU you would see inside a desktop computer if you open it up. Nowhere near as powerful, of course. So this is the main brain itself. So this is the main processor board. We've also got a smaller processor here and a couple of RAM chips here. Okay, in the same way that you might add RAM to your PC at home. So these RAM chips are fixed onto the board. So this board, this side of this board, is where the main, this is where your program runs inside these ICs. This is the main processor board. And these boards are all double-sided, of course. So you've got components on this side, components on this side. So not only are they double-sided, they're actually multi-layered. Like all sort of computer boards, there's actually many layers. But it looks like one single piece of board here is actually many layers of connections. But the components lie on both sides. So on this side, if you remember, we saw the LEDs, input and output LEDs, and on this side we've got the main processor and the RAM chips. You'll also notice this board has a little cutaway here so that we can access this, and this is visible through this opening on the cover, and this is the connection for the programming lead for the PLC. So when you buy this PLC, it comes with a proprietary lead that plugs in here, plugs into the back of your laptop with a USB connection. You run the software that comes with the PLC on your laptop, you write your program, and then you send the program over that network connection into this port. So that's the comms port for the sending the program to the PLC. Now when we looked at this earlier, we had 4 parts, so it's time to bring this bit back. This is the base of the PLC here. You can see it has its own electronic board in it, and this is the power supply. So this is what's called a switch mode power supply. So the PLC is supplied with whatever voltage you've specified when you purchase the PLC. It might run off 230, might run off 24 AC or 24 DC. But this power supply then takes that main supply and converts it into the different DC voltage levels needed to run this circuitry. You'll know, if you've ever opened up a desktop computer, you'll know that sitting in one corner in a metal box is the power supply for the computer. Does the same thing. Takes in your 230 from the mains and gives you plus 5 volts, plus 12, plus 24, that sort of thing for running all the boards inside a computer. And this is the same thing. So the power supply here gets its supply in and back out again to these boards through this connector here. So you'll see that if we were to mount this back down inside here where it goes, you would see that these 6 pins pass up through these holes and into this connector here, which supplies this board, and then out through these connectors to supply this board. So main switch mode power supply, which generates the different voltages necessary to run this electronics, probably mostly 5 volt and 12 volt DC. So that's pretty much it for the walkthrough of the interior of your PLC. So just to give you a quick recap, we had input terminals and output terminals. Every input has an opto-isolator on it to prevent electrical noise reaching the main processor. Every output has a mechanical relay on it to do the switching on and off. And then there's a main processor board here where we have the brain. and the various memory chips and the power supply itself for running it.